Testing, testing. Okay. Things are going good. Everybody having fun? Learning clever math? Learning the grown-up stuff? Do you wish you were back in the day where you only needed to worry about solving 5x plus 1 equals 11? Yeah, you're glad that day's gone? Okay. Good. And we still have about 5 minutes, at least by my watch. Have we got any general questions, just for the good of business? That's good. Did you all get my joke last time? Did you finally figure out why it was meant to be funny? Jacob, I think you laughed the first time. Did you like it?
I thought it was good.
Right. So you didn't need to think about it. You got it first one right away. You began to say something and it broke up.
Oh, I said I had to think for just a second.
Okay. I think that's probably everyone who's likely to be in this. We got a couple of stragglers. Oh, we just lost someone. Okay. I want to get started today on going over the change in variable stuff. We'll see how far we get, but tomorrow, that's kind of what I want to devote my time to as well. I can't guarantee it in every case, but I'm hoping that cylindrical coordinates wasn't a big deal. I mean, there's some footery bits, but most of it is pretty much a standard process. Would that be fair to say that you can fight through the coordinates without cylindrical coordinates without me doing too much work? The spherical's messier, and I understand that, so I might have to do some, maybe on Friday, we might do something on that as well. But what we're going to look at today is this change in variable thing. Oh, we've still got some people coming. It's analogous to changing the variable in good old Calc 2. And what makes it different is that you have two variables, not just a u sub, but a uv sub. And you're doing a double integral where you're doing two changes of variables simultaneously. So in the old days, it used to be, you know, the square root of x, x squared plus 1 times x or something. You do a u sub x squared plus 1 and off you go and do it. But when you do a double integral, that really doesn't work. So you have to do this all sorts of bits and pieces. And that's one of the things that makes it so long a question, if you get a full question. Thankfully, the homework's broken into little sections. So let's get started and show you the big picture, and then we'll start homing in on the little picture. Suppose you're doing a typical double integral over some region R of some function that's in terms of x and y, dx, dy. And that's what we're going to be using the double integral change in variable technique for. We're going to focus on double. It is possible to do a triple integral, but if you do a triple integral, you have to have 3 changes of variables. And trust me, the math just grows exponentially. You know, if you think these are long, double it. That's how long a triple integral would be, right? So that's what we're after. What is it equal to? Well, you're going to change the region that used to be in the XY world and called R into a new region called S in the UV plane. The function X is going to be replaced by a substitution. So X will be given in terms of U and V, and so will Y be given in terms of U and V. And then you're going to multiply by this fella. I'm not going into too much detail what this thing is yet, just writing it down. But it's a determinant of a 2 by 2 matrix where the 4 elements are made up of partial derivatives, du, dv. So there are a couple of features here that we have to be able to do to solve this. First thing is, you need to find x and y in terms of the other variable, the u and the v. Now, that's a little bit different than the normal way of doing it. Normally, you would say u is x squared plus 1. But you see, in this case, the x is a function of u and v, and the y is a different function of u and v. So that it's still a change in variable, but the perspective is different. Instead of saying u is a function of x and v is a function of y or something like that, what we're really doing is saying u and v are a function of x. You know, u and x is a function of u and v. Let's say it the right way around, and y is a function of u and v.
Is this just an example?
Yeah.
Right here? Okay.
Just a pure made up one. Now, first thing we're going to look at then is calculating the Jacobian. And the Jacobian is the name we give to this thing here. So we're going to assume that we already know this, and we're just going to get some practice at finding out who this guy is. So in this example here, you do the partial derivative of x with respect to u. You do the partial derivative of x with respect to v, the partial derivative of y with respect to u, and the partial derivative of y with respect to v. Now, I'm going to make an assumption which probably won't be true for all of you, but have you seen a matrix before, in particular a 2 by 2 matrix, especially if you've done 215? This is not a big deal, right? If you haven't, then it's a little bit different. A matrix, in this case, a 2 by 2 matrix, 2 rows, 2 columns, 4 different pieces. This vertical line either side is what we use typically, at least, to represent the determinant. And you calculate it by finding the major diagonal, which is those two. So you're going to multiply the partial derivative of x with respect to u with the partial derivative of y with respect to v. Take away the minor diagonal, which is this guy. And the minor diagonal in this case is the partial derivative of x with respect to v times the partial derivative of y with respect to u. Are you comfortable with the formula for the Jacobian, what it is, because it's the same formula all the time, and that these guys multiplied, take away these guys multiplied, are going to be the Jacobian? When I am finished, this thing will just be a function of u's and v's, or it may be a number occasionally as well. So let's see what we get here. If you differentiate this fella with respect to u, you get 1. If you differentiate it with respect to v, you get 2. If you differentiate y with respect to u, you get 2u. And if you differentiate partial derivative of y with respect to v, I believe you get 9v squared. So in this particular example, you're comfortable about where the 4 pieces came from. Right? Now, major diagonal goes this way. 1 times 9v squared gets you 9v squared. Minor diagonal, 2 times 2u, so you take away 4u. And that guy there is called the Jacobian. And that's the guy that fits in here. So see, this thing here is going to turn into u's and v's. In fact, everything here will eventually be in terms of u and v, the new change in variable guy. Are we good so far?
Based on the buildup, I expected something way grosser, but does that come in when we go to change the region?
Well, you're going to find that all the bits added up are grosser, but I'm glad you don't find it too gross. If you tried, thankfully we're not going to do, but if you tried a 3 by 3, can you imagine how horrendous that thing would look? You'd have 3 variables called u, v, and w, and you'd have a 3 by 3 matrix, which you would then have to calculate the determinant of. But no, I'm glad you don't think it's too bad. Well, that piece of it isn't, but there's a lot of pieces to it. Okay, so that went well, but I think I should do maybe a couple more of just finding Jacobians, just so we're comfortable with the process, and then we'll move on to another piece of the puzzle that you need to get to put this whole thing together. So, no particular reason. Let's suppose x is equal to 3u take away 10v, and y is equal to 50u plus a v. Actually, very nice Jacobian coming out of this fella. Sorry, can't take your eyes off this for a second, or you'll lose the place. So x, y, x, y, okay. Differentiate this with respect to u, and then differentiate with respect to v. Differentiate this with respect to u, and then differentiate this fella here with respect to v. And can I change this question? So all of that, I've just made the question a little bit different because I was hoping to show you this. Major diagonal is 3, take away the minor diagonal is 500. Technically speaking, 497. That is the answer, right? Is it?
Notation backwards.
Well, let's hope I haven't done that. 3, check. 10, yeah. 50, check. 1. Major diagonal 3, take away 500, negative 497. What do you think I may have done wrong?
Oh, I thought on the last one the Jacobian was dx over du,
It
dx
is.
over dv.
Oh, darn it in space.
The x's were
It-
both on top and the y's
It
were both
is.
on the bottom.
These are correct. I've just written that wrong. It is dx by du, which is still 3. And it is dx by dv, and it's still 10. Yeah. I wasn't even paying attention to my formula. The good news is I was doing the correct thing. Right. So, the reason why I probably distracted myself is I wanted to get a negative number here because I want to show you a little idiosyncrasy. The Jacobian is never allowed to be negative. So the symbol that we use to represent the determinant of that 2 by 2 matrix is also considered to represent that it should be the absolute value of it. Now, that won't make a big difference except if it is a number, because 497, the Jacobian must be positive. So if it's a number, like you do the calculation and the determinant's negative 10, right, for example, you will make the Jacobian positive 10. Now, what happens if the Jacobian is something like this one here? You would leave that alone, working on the assumption that you're assuming that it's positive. And that's a pretty big assumption, but we'll just assume it anyway because it's very difficult to prove when it is and when it isn't. And so,
would it be safe to track that, like if you're just writing it all out, like next to your equation and everything, with just keeping the absolute value around it? You're not going to get around anything weird if you do that?
yeah, if you, the sticking to the absolute value part, if you wanted to think about what I could do here, the disadvantage of finishing with that absolute value is it just makes the integration process later uglier because how do you integrate the absolute value of 9v squared minus 4u? It's a distraction rather than a help. But if you keep it going to the end and then the last line, you figure it out. And the figuring out pretty much is if it's a number, make sure it's positive. And if it's not a number, assume that the thing that you've got in front of you with all the u's and v's in it is positive because it should be. That's a very dangerous assumption. But in the questions that you're going to do, they are positive, so you don't need to worry about it. Now, I could change in the subject a little bit. Suppose my Jacobian was negative u squared minus v squared, which I believe none of your homework questions are, but let's just, for argument's sake, that was the case. That is not positive. In fact, isn't that guaranteed to be negative? So in that case, I would logically say that the Jacobian is that. I don't want to get too caught up in the weeds here. That's not going to happen to you, right? We are not going to, in the test questions or whatever questions, we're not going to spring upon you a Jacobian that isn't good to go. The only time that it's fair to do it to you, because I think you can see, is when the answer happens to just be a number. I think that's an easy one for you to deal with. But if it's got u's and v's in it, leave it alone and say, I'm assuming that it's positive and hoping that the math gods like me.
Why can't Jacobians be negative?
To do with the process of what they're calculating, they're really a bit like a scale factor. And so a scale factor is how much do you multiply something by? If it's a big number, you're kind of stretching it. If it's a small number, you're shrinking it. But it doesn't make sense to say that the scale factor is negative 2. You know, a scale factor is like times 2 or times a half. And so it needs to kind of be positive for the geometry of what it does.
Yeah, so basically, since we're calculating areas and volumes, right, we can't have an imaginary area or volume.
In a double integral context, many of those questions do represent areas and volumes, and therefore negatives wouldn't make sense. But you have to be careful that there are situations where the final answer, the double integral, can and will be negative, right? But not the Jacobian part. That must always be positive, right?
Gotcha.
We good?
Yeah,
Right.
thank you.
Yeah. It's just breaking up voice. So if you did ask a question, I didn't really catch it. Someone, no, you're just commenting on it. Okay. Right, let's do one more. And I'll try and get the formula the right way around this time, although I did the correct answer. Let's suppose U equals R sine theta, and Y equals R, X equals R cos theta equals R sine theta. Got it right. Do you recognize this guy? Isn't it polar?
Yeah, it sure is.
Right. Now, do you remember that the polar had a funny R, dr, d theta? You remember that? And we just said, look, put it there because it has to be there. Let me show you why it's there. Let's do the Jacobian. Dx by dr, dx by d theta, dy by dr, dy by d theta. I want you to think of the r and the theta like a u and a v, right? They're just letters. You could pick a and b if you felt like it. I wouldn't, but they're just letters, variables. Now, if you differentiate x with respect to r, you get sine theta. If you differentiate y with respect, x, I should say, with respect to theta, r sine theta turns into r cosine theta. Now, if you focus on the y, differentiate it, you get cosine theta. I'm getting these the right way around here. Well, technically, I've got them the wrong way around, but it's still going to work. This fella here, we're going to get negative r sine theta. Major diagonal, negative r sine square theta. Take away r cos square theta. I got these back to front, but that doesn't really matter because the answer is still going to be what I wanted. You recognize that that gets you 1, and the answer is negative r, and stick the little absolute value from it. There's the r that you mysteriously appeared in the polar. And actually, if you'd called this guy r cos theta, and you'd called this guy r sine theta, this would have come out even prettier. It would have been r right at the end. Now that means you could, if you felt like it, create some new geometry systems. For instance, maybe you could say the x coordinate is r secant square theta, and the, well, that'd be a bad choice. X is r secant theta, and y is r tan theta. Right, so imagine trying to describe a geometry where the x and y coordinates were described in terms of an r and a secant and a tan theta. Now, if you did that, you could create the Jacobian for it. Do you know you could convert an integral using the Jacobian change of variable technique and get the answer? The reason that particular one, which I just randomly threw at my head, was that I suspect strongly that that particular one I gave would give you a really ugly Jacobian, which would make it even harder to integrate the thing that you wanted rather than easier. This one has a nice value, right? It's just r. So if you can think of what's going to happen, won't this thing just be r, and this will be dr d theta? You've almost got your polar created from scratch. And if you've done the spherical, do you know the spherical can be shown as a Jacobian in 3D, and that's why you get all those funny rows and cosine phi's and things floating around. Okay, well that was phase one. How do you find Jacobians? Now, with a bit of luck, I should have something set up. Let's see if we have. Yes. So, are you seeing a screen with some, it says 6 and 15.9 change of variable? Is that what you're saying right now?
Yeah.
Yep.
Right. Now I'm going to make it one page because I've got a bigger monitor than you. You probably can't see it. That's probably overkill. A compromise somewhere in the middle. Right. Now, this guy that is number one is virtually homework question one, and it took me 2 pages to do it. It took me about an hour to type it. So I'll let you wonder about that and look at it for yourself. I'm not going to spend a lot of time in that kind of question because I'm not going to expect you to know a lot about it. Right, here's our Jacobian we've talked about. Just nice and big. Here's an example of it. First one. Here's another Jacobian. Here's the third one. There's my little rule. Call it 4UV, but right at the side, provided 4UV is greater than 0. That's just to cover your butt mathematically, right? I'm still going to call it 4UV, but that's just to make myself feel safer. Right, there's the version that I should have done, the r cos theta, r sin theta. And you see it comes out really nicely. And here's the weirder one, say u tan theta and say u secant theta. And no, actually it came out better than it could have as a u secant. Now at this point here, we've got the, what's the phrase I'm looking for? Yeah, we've got the general formula. The double integral in terms of x and y is now going to be transformed into a double integral in u and v. We've spent a fair amount of time getting this one piece done. I'm going to spend just 5 minutes getting this piece done. Then we're going to talk about how do you convert the r to the s's. And then once you know that bit, and this bit, you're now good to do the whole question, right? So phase two, let's focus on this bit here. This bit's not too bad. So imagine, so I'll close this off. Imagine that I had a function, a double integral, and it was x squared plus y dx dy. And we have x is equal to u plus v squared, and our y is equal to u minus v. Then this bit here is the f of xy, right? So what does it become? Well, it's basically just a straightforward substitution. That's what x squared becomes. Add a y. That seems reasonable. The formula x squared plus y gets converted into u's and v's. The x's becomes u plus v squared, all squared, and the y just becomes u minus v. Now, I would have to multiply this darn thing out. And we now have that piece. It's more laborious than difficult. Would you agree? You just replace the x's with whatever x is equal to. You replace all the y's by whatever it is equal to. Since you know you're going to have to integrate it, you're probably going to have to spend some, multiplying, distributing, collecting like terms, factoring, and, doing all the kind of style point things that you would have to do to try and get it into a decent form. This is just ugly, but it's not a difficult thing to integrate. Would you agree? It's not a difficult thing to integrate. Now, imagine there was a double integral over some region R. It was x squared plus y dx dy. Then it would be another double integral over this region we haven't figured out yet of this horrible mess, which I'm just going to call ... The Jacobian of it, du dv. You see, it's beginning to take shape, isn't it? The double integral in x's and y's is slowly being transformed into a new double integral with u's and v's in it. I think the goal you kind of have to convince yourselves of is the reason you have to do this is that some double integrals, probably not this one, but some double integrals, you can't do them with x's and y's, right? The integrals are so ugly or just not integratable that you're stuck. And therefore you have to use a u sub technique. We're just doing a u sub in the in the double integral world. I mean, so that's when you would use it, right?
How would
cool?
the x and y values?
You're broken up. It sounds like something about x and y values is all I caught.
How would you find those equations that define x and y?
That is a very good question. Depends on the question. There's not one specific version. I'll give you an example of two of the most likely, well, three. First one isn't really a problem. They tell you. They just tell you, like I've been doing right now, x equals this, y equals that. That's a baby question, right? Hey, thank you. Secondly, they describe the region R something like this. That's a bad choice. Make that 0. Yeah. Now, this is the region R being described by a sequence of, 2x plus y is 4. And, well, I mean, they might break that up. I've seen them do it this way. 2xy plus or equals 0 to 2x plus y equals 4. It's the same thing. It's just convenience, right? If they show you this, and it's clearly the same guy, but with a different number, make him your U and make him your V. Now you might say, but that's not what I want. Well, you need that to start with, because if you know that U equals 2x plus y, and you know that V equals x squared minus y squared, then you have to do a whole load of algebra and rearrange it to x equals some function of u and v, and y is some function of u and v. So that would be your second situation. And your third situation, they will give you a picture of what R looks like. And you will use that picture to predict what your U subs and your V subs are going to look like in terms of X or Y. So we aren't, well, where are we? We're about halfway through, maybe even not 40% of the way through this process right now. And because, the best is at the end, as you can imagine. This is not, some of these are not going to be simple. So let me do one more of the conversion of the function things, just so we can say, look, that's not a difficult part, right? And see where we can go from this. So let's suppose I have a function f of xy, and it's x squared minus y cubed. And x is u plus v, and y is u minus v. Okay. In this case, it would be u plus v squared, take away u minus v cubed, And I'm just going to say ... here. Can you imagine that would just be one ugly thing when you finished? But you could do it. Now, I think this might be a good point for me to bring in, how do you get the U's and V's? So let's actually do a physical one like this. Let's suppose that you've got a region in XY space that looks like a rectangle on its side. Could be a parallelogram, something like that, right? And this line here is y equals 2x plus 3, and this line here is y equals 2x minus 2. Can you imagine? You could do that, right? You're either told it, or I could just give you the coordinates of those 4 points and you could find those two. And then these two lines are also parallel. And let's suppose this fella here is 6 minus x, and the one next door to it, let's say he's 10 minus x. So this is our region R. And this region is going to generate our U and our V, right? So these two guys here are parallel. You agree? If I write down y equals 2x plus 3, and underneath it I write y equals 2x minus 2, although that's the way you write the lines, that's not helpful for what I need. I'm going to rewrite it in this format. Would you agree that this is the same thing as that? Agreed? Now, what does that give me? See this little fella here? Let's make him U. And I'll put a little bubble around him to say, I know U in terms of X and Y. Later on, that's going to help me to get X in terms of U and V. Now, the other two lines, they were y equals 6 minus x and y equals 10 minus x. And they're going to become y add x equals 6 and y add x equals 10. So that is going to be my second guy. And I'm going to call him v equals x add y. Are we good so far? Now, for us to do this, I don't want to know what U and V are in terms of X and Y. I want to know what X and Y are in terms of U and V. So that's what I'm going to be dealing with in a few minutes from now. But while I'm at it, let me tell you something that you get for free. Do you notice that these two parallel lines represent the U values, and these two parallel lines represent the V values? When we do our double integral, the U is going to be from -2 to 3, and the V is going to be from 6 to 10. You see, I've actually got the limits of integration of U and V, because the U is between -2 and 3, and the V is between 6 and 10. You okay with that? Right, now, back to the puzzle. This is an algebra game. This is probably one of the simplest ones. I'll call this equation 1. I'll call this equation 2. We normally solve systems of equations with x's, y's, and numbers, right? That's the usual way we solve an equation, right? So you're more used to that being 5 and this being 10, and you solve for x and y, right? I'm going to use the same strategy to find out what x is in terms of U and V. and then what y is in terms of u and v, because that's our goal. X equals this, y equals that. Now I look at these two equations. What would happen if I took the first equation and I subtracted the second equation? Well, u take away v, this guy take away that guy, let's see what that would look like. Y take away 2x, subtract this fella. The y's cancel out, and I'm left with negative 3x. So just like a system of equations here, do you see my goal is to get rid of the x's or to get rid of the y's, whichever one's easiest. Now, then won't that make x negative 1/3 u plus 1/3 v? And I now have one of my two substitutions. Right, divide both sides by negative 3. How am I going to get the other one? I know that x is a negative 1/3 u plus 1/3 v, but how am I going to get the other one?
Plug it into 2.
Okay, so if I plug it into 2, I've got v equals x, which is this guy, plus y. Add that to both sides, take that away from both sides. There we've got our second guy. So you were asking, how do we get these x equals y equals? Well, this is one of the ways you can do it. Can you see that what you try and do is in the region R, there's going to be some information that gives you a clue to who you're going to make the U guy and who you're going to make the V. And it's always based on the fact that if a shape is made up of, you know, most of these questions end up having 4 sides to them just because of the symmetry of it. But you can use this 2 guys here and the 2 guys here as like, whatever this equation is, it's only going to differ by a number. So you make this equation here your U, and this other one that's going the other way, you know, the ones that are going this way, they might differ by a number as well. You make them your V. Are we good? Any questions about that process? Because it involves us taking something quite geometric and doing some basically solving system of equations where there isn't a number in sight, everything's x, y, u's and v's. I'm going to move on. Let me do another share. And can I show you that here? Okay, so the only part of the process that we haven't talked about yet is, although we've kind of indirectly talked about it, is the region R has to be transformed into a region S. In the region R, the original integral might be quite messy, but the region S almost always ends up being U goes from 5 to 7 and V goes from 10 to 20, you know, that kind of thing. That's kind of the goal. So here is an example of a question from start to finish. Now, it's got most of what we need in it, but not everything. Okay, so here we go. We're going to do the double integral over a region R of 6x plus 9y dx dy. R is a parallelogram. These are its 4 coordinates. And we are getting the freebie one. What's the freebie one? The x equals and the y equals is given to us. So this is nice because it's one less job we need to concern ourselves with, right? So what I'm going to do now is I'm going to find u and v in terms of x's and y's. Now you might think, why do I need that? I need it because I have to transfer this region R into another region S. So let's see what it looks like. Very similar algebra to what I just did, right? If X is this guy and Y is that guy, do you see if you take X and subtract Y, you end up getting, oh, U. And that means U then can be X minus Y, and if you substitute into the other one, you get V, and it ends up being that. So we have managed to take the original piece of information, which was this guy here, right, and convert it into that. And you might be thinking, why did I need to do that? I don't need it for the Jacobian. This is great. I want this guy for the Jacobian. What I need it for is to rearrange the original space to see what it looks like. In other words, how do you take the R and find out what it looks like in the S world? Right. That's what the shape looks like in XY coordinates, right? It's 4 points joined together. It looks like some kind of parallelogram rectangle beveled in a corner. Now, if you try to do a double integral of that, you're dead in the water. Typically, wouldn't you do little vertical rectangles and move them from left to right? Can you see up here, it's these two guys, and then it changes to these two guys, and then at the end, it changes to these two guys? Can you imagine how difficult that would be to describe? Right. The normal XY method just kind of falls apart, and that's without taking into account anything else that would happen. So how do we get the new region? How do we find out what the new guy is? Well, do you know these two guys here that we found? The U and the V that we just found? We're going to use them. When you take a shape in the XY world, right, the two-dimensional XY world, normally all you need to do is find out what happens to the corners. Find out where they move to in the UV space. So XY coordinates are now going to get transformed into where they are new location in the U and the V. So for instance, the U is going to be the X coordinate take away the Y, and the new location for V is going to be 2X add Y. So you want to take this point here, UV, let's see what happens. -3 take away 6, -9. 2 lots of -3 add 6, 0. And if you check them, these 4 corners become these new guys. And when you plot these new two guys, do you see what the region S looks like? Do you see it's now a rectangle? Aren't rectangles the best double integrals in the world? Because your limits of integration for U and V are just start at this number, -9, and finish at this number 9, right? Use V's. So that's us done the transformation part where we found out what the new region looks like. Almost every question you're going to do, these two guys here are always numbers. So that's something, right? The double integral is going to be numbers in both cases. Now, changing variable has a guy here, has a guy here. We got the x's already, so we should be able to figure out what f of xy is. Hopefully it ends up being this fella. What's the Jacobian going to look like? A third, -2/3, a third. 1/9, take away -2/9, so 1/9 add 2/9 is 3/9. The Jacobian just ends up being a nice number, a third. The double integral, this piece here turned into that. This Jacobian bit is the third, du dv. And what's the new limits of integration? -99, -99. So the original integral in x's and y's has now been transferred or transformed into this guy. Now, I've actually done the work, and who knows if I've done it right, because I just did it before you came, so it was pretty quick. But the process is right. Can you see that that integral is not a hard thing to do, right? It's just add 1 to the power, divide by new power kind of thing. It's not an issue. But the work involved in getting that guy, Jacobian, what's the new region look like so you can get the limits of integration out of it? Change the f of x, y into u's and v's, transform your integral. And then once you get to kind of that line here, the one that looks like this, to me, once you get to there, the question's over. I mean, it's just normal double integral stuff that shouldn't cause you too much grief. I think that question, or at least the version of that question that we've just talked about, would probably take you about 20 minutes, you know, because the amount of things that you have to do and to get it right. So I'm a bit apprehensive about my answer being 0, but I'm going for it because, as I said, I just finished it a few minutes before we came online. It's okay for a double integral to be 0. Kind of weird, but it can be done. Can you imagine the floor being xy and z being up and down? Can you imagine a shape that half of it was above and the other half was below, just like in Calc 2? Couldn't the volume above kill off the volume below? Now we're talking about not physical volume, but like volume above the xy plane. So above would be positive and below would be negative. And so I can imagine a shape that had a cancel out. So I'm not saying it's not 0, because it could well be 0. It just was a bit surprising. Well, we've only got a few more minutes left here. I've probably burnt a few of your brain cells trying to keep track of me as I zoom through. I'm just about finished this one. I just want to do a double check on the last bit to make sure that my calculations are correct. And then I'll publish this one in Canvas so you can look at it slowly and some of the examples as well. And if I have time, I think I'll add one more of these, you know, from start to finish, because I think if you see 2, you're more likely to pick up patterns of how it's done, because there are different versions of these questions. I've seen questions where they give you the integral, but they don't tell you this fella. They tell you u is x plus y and v is x minus 2y, you know, something like that, which is really good for the transformation, but is really bad for the Jacobian, right? One version you need for one piece of the process, but you need the opposite version of it when you want to do, say, the geometry part of it. As I say, any questions? Has it lived up to my expectation that this is going to bite your bum? Maybe?
Oh, yeah.
Oh, yeah, okay, that's normal. Trust me, you will need to fight your way through 2 or 3 of these, and you don't actually get that many, although there's a few questions in section 3. Half of them are just find the Jacobian, and that's it, right? So they're not really long questions. So you're going to have to get all your experience from a few, you know, start to finish questions, just so you can do the process. And if you've got time, I would try and find as many other examples just to get into it, because the algebra can really bite you as well. Okay, I think it's time for me to say bye. Hope everyone, it was worthwhile. I'll see you tomorrow. Tomorrow I want to go over another question from start to finish, take about 20 minutes. If I do 2, that's 40 minutes, and that gives us 10 minutes for spherical, but we'll balance it whatever way you want. If you want to spend half an hour on spherical, we'll do that, you know, and do one question on the others, if that makes more sense to your issues. Okay, usual then, anybody who wants to ask me a kind of one-on-one question, just hang about until everybody's gone. Trying to remember, I did send out, if I didn't send out the email, you know to go and look at Canvas, and it'll tell you when on Friday, because I can't tell you off the top of my head. But you know where to look. And it's got the link there as well, so if you go there, you've got everything you need. Right. Okay, bye-bye. I'll wait for you.
Thank you.
You're welcome. Hi, Andrew. Do you have a question for me? No? Okay.